All right, thank you.
Everybody.
It is quite clear that the sustainability and the affordability of going to Mars is very much in everyone's mind because, you know, let's face it, even if we can make the right rockets and all the infrastructure we need, we still need the money to make it happen. The next panel is going to discuss that, and I'm going to hand you your... To be practical. The moderator, Jason Crusan, is now the one I'm going to introduce to you, and he will introduce the rest of the panel. Now, how to sustain mission goals, acknowledging the challenges, but even more so seeing the opportunities, is what Jason Crusan is going to share with us. His job at NASA is to find innovative ways to get humans to go to Mars and explore on Mars. And one of these innovations, public-private partnerships, is what his job is all about. Letting new commercial space companies take over where they can and encourage them in doing so, all to make the presence of humans on Mars and in space reach further. Jason, please introduce your panel for us.
Thank you. So we're going to walk through, my set of colleagues here will walk through a series of analyses and such. So I'm joined here by a couple folks, and I'll introduce them now, and then I'll allow them to hand off as we go down through the various discussions. First off, I got Professor Ali Dweck, who is a professor of aeronautics and astronautics at MIT. His research interest is in strategic engineering of complex systems for long-term futures. He's published 3 books and over 200 papers and an associate fellow of the AIAA and former chair of the AIAA Space Logistics Technical Committee. I'm joined after that by Brand Griffin, who's a senior engineer with Gray Research at Huntsville, Alabama, where he supports Marshall's Advanced Concepts Office. Early in his career, he worked with Boeing on the Space Station Freedom and Lunar Mars studies back then. More recently, he has developed options for cislunar habitation and currently leads a team conducting commonality analysis for Mars exploration vehicles, exploration crew cabins and such. Lastly, I'm joined by Candace Goodliff, who's an aerospace engineer at NASA Langley with a space mission analysis branch there. Her primary roles are system analysis for conceptual design and sizing of human and robotic spacecraft mission and space analysis and the overall campaign analysis for us. And you'll see these different aspects and disciplines each of them bring to the problem that we're all talking about here today. I'm going to start it off giving you a little bit of an overview of NASA's activities related to our Evolvable Mars campaign and where some of our thinking is at. I like to always start with an Apollo image. Famous photographer joined in taking a picture of somebody who's in the room here with us today. And I think this concept, this construct of human spaceflight is one that bounds the way of thinking that we go about today and is in some ways wrong. And it is that singular destination, singular purpose, one goal kind of objective that I think we struggle with, that we need to actually expand the way we think about human spaceflight wider than that into multiple goals, multiple sets of objectives as we branch humans into deep space. Our toehold with that today is the space station. The space station doesn't have a singular goal, but rather a set of goals. I summarize them as 4 primary goals. Obviously, advancing the technology we need to send humans into space is one of those. Understanding the biology and biological effects on human systems, for the human to do extended presence in space is another. The fundamental science objectives that they're advancing today for our on-ground applications and ground-based benefits that we get from space station, kind of off the Earth, for the Earth type work that we have going on there. And the last category is actually expanding of economic markets in space and building a space economy off the planet. And so you see station is a much more complex human spaceflight set of goals, which I think we also need to think about our overall Mars strategy in that construct as well. It's not just about getting there fast and being first or planting a flag and footprint, but rather how to do that in a sustainable and affordable way. And it was good to hear JPL's latest analysis this morning. So I'll build upon that discussion that started our day. We're on this prolonged journey to Mars. We're basically moving from the space station phase that we have, where we're extremely Earth reliant, moving through a proving ground period of activities into the Earth independent phase, and figuring out how to live far from Earth with no reliance back to us. And part of this, you'll see in my colleagues' analyses, becomes a logistics problem, as you saw some previous talks talk about. And logistics of actually sending all the cargo, logistics and the people and such on a sustained human presence is a big challenge we're facing. Also, a lot of folks focus in on Obama's speech back in 2010. They focus on the dates of 2025 and in the 2030s. But more importantly, I think before that, he said something that really resonates with me, which is sending people further into space for longer periods of time, extended periods of time, and even gets into that maybe even indefinitely, and talking about that in a different frame. So to me, the dates and date constructs are less important, but rather the sustainable presence out there, to me, is what resonates. As far as a snapshot and some updates that are coming from NASA, we have in the past published a document called Voyages, and we talked about this kind of endeavor of sending human spaceflight and how all these different themes in human spaceflight link together. We are doing an update to that. It's a document that is currently draft titled Pioneering Space. It's going to be this top-level kind of strategy and talking about how we stitch together these different strategic thoughts of extended human presence into the solar system. It's going to have key things in laying out our principles, the strategy, the technical challenges that we all know well, current plans and actual progress that's being made towards those, and be out there as a kind of a living document that we can all think about and try to rally behind. One of the key things is we built a set of strategic principles, and I won't belabor these because many of you have seen them many times. There's 7 principles here. There was a good discussion on what affordability was, which kind of alludes to the first bullet up there. Building a fundamental architecture that lives within our financial means that we have in the near term, but does count on inflationary growth over time. You can't do this with a flatline budget, as many have laid out, and we do need some level of inflationary growth, but we're not going to be getting there. Next one is exploration enables science, science enables exploration. In the past, we've always talked about separate activities. I think we, as a community, have come together and actually looking at more synergistic way of science and human exploration working together. And we're seeing real tangible missions now that are cooperating in ways that we never thought of, even just near term several years ago. The balanced technology is the next principle. How do we apply high technology readiness level activities while still making the investments we need for the long term? That's a key aspect, and we got to ensure that we don't cut our future seed corn for these missions. The next one is cadence, near-term mission opportunities, cadence, launch cadence. We can't have large breaks in time where we don't have activities and flights going on. So how do you ensure an architecture that considers flight rates and constant excitement and continued progress into deep space in that overall architecture? Commercial business, we're now playing catch-up, I would say, with Station as we're trying to transition towards the end of Station over to commercial operations. We need to actually envision commercial activities right from the very beginning. And how do we engage them in our fundamental architecture from day one and expand that economic space economy work into our overall human exploration plans as well. Multi-use evolvable infrastructure. You see elements of the multi-use. To me, there's 2 categories of multi-use. There's one DDT&E, design, development, test environment, where you do that once and you have a production line and you assemble them on a regular cadence. You see that with launch vehicles and those kind of things. The other side is real reuse. So how do you do staging and bring habitat elements back and actually reuse them on multiple trips, getting into, near cycler type activities, and actually start planning that reusability there. I don't think that's a hard technical challenge for us these days. As we're showing that we can build habitation structures that have 20, 30-year lives today. You do need to do refurb and commodity refresh, but beyond that, structurally and all those kind of things, that's within our grasp today. The last is, again, we're not going to do this alone. There was a good question about international involvement and how we involve the internationals, and there's multiple efforts engaging those folks as well. So what we're taking a look at is we have DRA 5.0. It was published. There's a lot of things in it that we've now found that are fundamentally different. When it was written about and published at that period of time, we didn't understand the water cycles on Mars, and we hadn't actually found water on the moon. So how does ISRU play into things? DRA 5.0 obviously had oxidizers and makeup gas and those kind of things in its architecture, but is there a further expansion of in-situ resource utilization that could actually happen and be enabling for us? The split versus monolithic hab pre-emplacement, you saw elements of that in JPL's study. This kind of pre-emplacement of hardware ahead of time. I think there's a lot more confidence in the architecture and design community and systems analysis community that that's something that we should be taking advantage of even more than we were in DRA 5.0. Other stops along the way, Phobos, Deimos. Yes, those have been looked at before, but they were never really strongly considered in our overall human spaceflight architecture train analysis, and we're revisiting that today. So our Evolvable Mars campaign is a whole set of folks from across NASA, all the NASA centers, and mission directorates working together on that. We also strongly engage our international partners through the International Space Exploration Coordination Group and analyze and work with them on different options and priorities that they have. Industry engagement through BAAs and RFIs. You see us putting out a lot more public calls than we've ever done in the past, and all of those are helping us inform our overall architecture. And then the various analysis groups like LEAG, MEPAG, and small body assessment groups. All those are folding into our groups, and EMC is setting out this whole set of analysis of how do we update some of our fundamental assumptions that we had from DRA, and how do we come to concrete near-term decisions in the next 1 to 5 years that are in our budget, potted in things that we're building, how to come up with the acquisition strategy for the 5 to 10 year range type stuff, and then how to keep that trade space open in the 10 to 20 year range and be opportunistic and lower the transaction costs or the switching cost from one element to another in the future. It's had a whole host of findings, and I won't go through all of them. But key things like aggregation orbits, the Lunar Distant Retrograde Orbit, we've done quite a bit of analysis on that as a staging point. There's quite a bit of confidence in that being a good staging point both for build-up and return. Orion Block 1 is sufficient for most of our architectures and analysis. So once we get Orion flying, we don't see large-scale increases on Orion capabilities, but rather kitting for mission-specific applications for that. The solar electric propulsion trade analysis, I won't go into detail with that because you saw a lot of it from JPL's study. SEP is changing the way we look at a lot of our architectures. And instead, we're having discussions about what is the power level versus whether it exists or not. That's a good, productive debate to have. I talked about Phobos and Deimos. You see a lot of emphasis coming out of this. It's not so much emphasis, it's rather letting Phobos and Deimos catch up in our knowledge, broad knowledge base, to be able to consider that as a staging point for our overall activities. So really what we're focusing on is where are the commonality between the Mars vicinity destinations, be it orbit, Mars moons, and the surface. There is quite a bit of commonality, and you'll hear some of that commonality from Bran here in a minute. But things like habitation, there's a vast amount of overlap in habitation, whether you're going just cislunar space, the transit vehicle, or Phobos, or even to the surface. The amount of commonality is obviously far greater than the uniqueness of those systems. LDRO. I don't really probably need to talk to you guys much about trajectory type analysis, but this is a gravity well map that we use to help communicate the value of LDRO. And what you see there is the gravity well of Earth and the gravity well of the Moon. You see the Lagrange points, L1 and L2, and you see the region of where the family of orbits of LDROs exist. And it's really at that gravity neutral point there, and the stability of that orbit is something that we're finding very intriguing to us. At the same time, that's also a great point for assembly. And because you don't take a whole lot of delta V and you don't use a lot of logistic flights to be able to keep things there while you're doing that assembly or refurb. So you could think about the overall habitation system sitting in LDRO, maneuvering out of LDRO on an outward bound trip, and then being parked back there for refurbishment on the way back. At the same time, we're looking at Mars orbits and trying to determine the advantages, disadvantages of all the various options there. You see a one-sol orbit, which is what we've been traditionally looking at when you take a SEP and chemical multi-stage approach. We can get into a one-sol type orbit. But we also are considering things like a 5-sol orbit, which is where you get a hybrid stage of SEP chemical and you're actually as one integrated stage. What are the advantages of that? I mean, other things like hyperbolic rendezvous and those kind of things are also on the table, and you see that there. And I don't think we actually need to make that decision today, but rather continue to analyze the advantages of these different staging points. So we analyze the work in the EMC by a set of questions. This is the set of questions. This page and the next page are the set of questions we're looking at. You're going to see a flavor of those questions by my 3 colleagues here, and I'll let them get up here in about 2 seconds to actually walk through that. The first, though, pioneering extended human presence. The in situ resource utilization trade is part of that overall work. Brand's work is part of an overall effort on habitation, commonality, and modularity. And there's 2 approaches of small modular HABs versus large HABs, and the competing pros and cons of those options that are out there. And Brand's looking at the smaller HABs and the commonality among those. And then you get into overall SEP trades and a number of those activities, and you get into where are the viable habitats and what does a viable habitat system look like. Can we actually survive 1,000 days in deep space, and some other key questions that we're looking at. And then you get into sequencing and how does this actually follow through all the way through from what we're flying today to an end result of getting to Mars. And Candace will touch on a bit of that area as well. So with that, I'm going to turn it over to Ali to give his a very intriguing look at a recent paper and publication that they've been working at MIT.
Thank you
Thanks,
very
Ali.
much. Thank you. Harley, can we use your high-power laser? Okay, it's a great pleasure to be here. I would like to acknowledge, first of all, our doctoral students here. Guys, raise your hand. It's great, those of you that have the pleasure to work with at universities, you know that it's the graduate students that are really the brain power behind this, and it's wonderful to be here and share a little bit the role also that universities can play in this, because I do think we have an important role to play both for the future workforce, but also to provide somewhat of a rigorous and unbiased view into this. So, Jason, thanks for the invitation, and I'd like to share a little bit of our thinking around ISRU. Thank you. So the question is, what can ISRU's role be in the larger picture of human exploration to Mars in particular, and not just for the initial landings, but really to establish a permanent presence? And what we think is needed the most is a change in perspective. We've really been quite successful, of course, in lunar exploration and Martian exploration robotically on a mission-by-mission basis. And that is good, and of course, we plan mission by mission. But if we think long-term, we think that we need to think of this as a network problem. And once you think of it as a network, as a logistical network, there's a change in perspective, and the decisions that come out of that perspective could be quite different. And so let's think of it as a network supply chain problem. And of course, on Earth, exploration on Earth, for example, Antarctica was mentioned earlier, really changed radically once we had logistics technologies. We were able to harvest local resources and so forth. So it's that network perspective that I'd like to bring in. And when you think about it as a supply chain network, the question is, well, where does the supply come from? And fundamentally, we have 3 sources of supply. Of course, the Earth itself. And when we talk about a sustainable exploration over time, think of this as an umbilical cord back to Earth. That umbilical cord should shrink over time. It doesn't mean it has to go down to 0, but the umbilical cord to Earth, the IMLEO, injected mass in LEO, should be as low as possible. The second, of course, is recycling. And this is an exciting area, recycling in ECLIS. Recycling can't be 100%. Bill Gerstenmaier mentioned yesterday the current loop closure rate on ISS is about 85% for water, and it's very expensive and complex to go higher. So there's some optimal recycling rate. And then local production, ISRU, which is what I'll talk about next. So ISRU's role in the larger logistics network. So if we think about it as a network, at least the Earth, Moon, Mars system, this is roughly what it looks like. What you see here is various kinds of nodes, surface nodes, the Lagrangian points. Also, Jason mentioned the DRO orbit. Those, you can all think of them as nodes in the network. Now, this, unlike a supply chain on Earth, this is a constantly moving network. So the delta V's change, and so the dynamic nature of this network is important. Because we're showing this as a network, but that doesn't mean that every node in this network is actually used. These are potential nodes, and every edge in this network, behind this, there are a lot of choices in terms of propulsion and trajectories. And the question really is, for a particular destination, duration, and exploration objectives, what is the best use of that network, and what elements and resources flow through that network? And so let me talk a little bit about the mathematical formulation of this, because this is, we think, one of the exciting sort of new findings is that you can formulate this as what we call a multi-commodity network flow model. The idea here is that we have a long list of, we call them commodities, but they include, the vehicles, the elements that we saw, for example, in JPL's presentation, food, water, the crew itself. Those are all commodities that interact with each other through this network. And each node here in this network has an inflow and an outflow. And there's a couple of tricks also that are necessary. One is the idea of self-loops. So you have flows in and out and production at the same node. And then you have multiple choices in terms of flowing, making choices between these nodes, different types of trajectories and so forth. And you have to really be quite explicit in terms of what it is that you're trying to optimize or minimize in this network. And so in this particular work, we're very focused on IMLEO, injected mass in low Earth orbit. We want to drive that down as much as possible. There's other objectives, of course, like the budget that we heard about in JPL's presentation, operational risk as well, and you'll have trade-offs between those. All right, so let's talk a little bit about a solution to this multi-commodity network flow problem for Mars exploration. And so in this particular formulation, what you do is you say, we want to explore at Mars. You pick a location, and you say, this is the duration, the crew, and the activities that this crew will perform at Mars. That essentially sets your demands at the destination node. And from that, we then have to satisfy those demands through the provisioning of resources, through all the flights. But we don't pre-specify what vehicles, what nodes are going to be used. And when we first solved this problem, and you can see this optimal solution here on the left, it was kind of surprising because the moon, lunar ISRU, turned out to be very important. And when we first saw this, we thought, well, maybe there's some mistake here in the formulation. And we really dug into it and found that lunar ISRU, as an enabler of Mars exploration, can have a major role to play. Of course, ISRU on Mars itself, primarily for consumables and for the ascent fuel, is essential, and this is also part of DRA-5. So that wasn't surprising. But what is surprising is that in this case, if you look at the actual trajectory that both the cargo and the crew take, Earth-Moon L2 turns out to be a very interesting staging point for a fuel depot and a place to go to Mars. And the reason for that is the gravity wells that Jason showed. The amount of energy it takes to launch from Earth is humongous. And if we had the ability to generate oxygen and fuels and perhaps other supplies on the moon, it really is a game changer. And so in this particular architecture, outbound from Earth-Moon L2, low Martian orbit, and then landing ISRU production on the Mars surface itself, and then on the return, we do not go through Earth-Moon L2. Now, what is the benefit of that? And I'll talk about it a little bit more in detail, is that you can radically reduce the IMLEO requirement by using ISRU. How good does the ISRU have to be? In other words, what level of productivity does the ISRU have to be able to provide to really be interesting? And that's what you see in this chart here. So on the x-axis, we have the ISRU resource production rate expressed in kilograms produced per kilogram of plant mass per year. So how much the multiple of how much of its own mass an ISRU plant can generate per year is really the most important measure here. And what you can see is that we made a baseline assumption of 10. In other words, say a 1 metric ton ISRU plant can produce 10 metric tons of resource like oxygen, which is very favorable. But even if you're not quite as good, ISRU still plays a large role. In fact, and we've shown this in several analyses, somewhere between 3 and 4 kilograms per kilogram of plant mass per year seems to be a critical threshold where if you can get better than that, ISRU really starts to play a major role. Let me talk about the MLEO savings. Once you take into account the time dependencies, the time windows, and so forth, you can start looking at the incremental benefits of ISRU in terms of enabling different types of ISRU. So starting with the baseline of DRO 5.0, which, yes, DRO 5.0 uses Martian ISRU for oxygen, primarily for ascent fuel, and then gradually enabling more and more types of ISRU on Mars, but also water on Mars, methane on Mars, and then eventually the lunar ice and oxygen that I just mentioned before. We believe that up to 48% reduction of MLEO can be achieved. Now, the price that you pay for that is certainly an increase in complexity because you have fuel depots, you have refueling operations, and so forth. But if you're thinking long-term about long-term sustainability, it's this MLEO that is coming from Earth. And the commodity and resource resupply infrastructure that's on the Moon and Mars at some point becomes almost self-sustaining. Okay, so the other thing that we looked at is the interdependencies among missions. So if you're only deploying the ISRU infrastructure for Mars exploration and Mars colonization, that's one thing. But if you can start reusing and repurposing that ISRU infrastructure for other missions, then you get additional benefits. So what this shows here, just focus on this number, the minus 19%. This is essentially an additional benefit you get from carrying out a NEO mission before you go to Mars. And so the 19% benefit comes in from the common use of the space infrastructure. That's a 6% improvement. And then 13% of that comes from the longer time horizon that you have for producing ISRU over time. So this is the ability to really pay off or amortize your ISRU investments over not just the Mars missions, but NEOs and other purposes as well. A lot of details, of course, need to go into the actual ISRU development and modeling. This is an example of a particular technique on the Moon called Molten Regolith Electrolysis, and essentially also known as electrowinning. So in this particular technique, you heat up the regolith to pretty high temperature, 1500 kelvins, and you separate all the metal oxides from the oxygen. And the benefit here, while it is quite energy intensive, the benefit is you get most of the oxygen out of the regolith, plus you get some metals which you can potentially use in manufacturing, which I'll talk about next. One of the key questions here is, well, again, how good is the ISRU? What can it produce? And what are the economies of scale? So if you look at this curve here, this shows you the annual oxygen production level through this process, molten regolith electrolysis, and then the effective productivity in kilograms of oxygen per year per kilogram of plant mass. And you can see that as you scale up your ISRU, it gets better on a per unit basis. That's what we call economies of scale. And at 10 metric tons a year, we start approaching a level of roughly 7 kilograms per kilogram of plant mass per year, which is above this threshold, this magic threshold of about 4 that I mentioned. So this looks quite promising and very encouraging. And this is roughly what a 10 metric ton plant would look like on the Moon. So very briefly to wrap up, additive manufacturing, very exciting. We now have a 3D printer in space, and it's been starting to produce parts. And so what we looked at and what we're going to present in a paper this summer is, well, what if you combine adaptive or additive manufacturing and ISRU together? In other words, not only are we going to 3D print parts in space, but the feedstock for the additive manufacturing is going to be produced from ISRU. What benefits could we get? And you can see here on this chart that over time, the cumulative savings by being able to not bring all your spares from Earth, but being able to produce on demand through ISRU feedstock at Mars really increases substantially. And so the difference here between the solid and dashed line is whether or not you bring the feedstock with you from Earth. And then the difference between the blue and the red is the level of precision or the complexity of parts that you can actually make. So ISRU couples with propulsion, but ISRU also couples with the ability to make your own spares and eventually move to truly Earth-independent exploration. So let me just summarize here. ISRU, we believe, and the numbers show us, can be a major enabler of sustainable human exploration. That doesn't mean the ISRU has to be perfect, but it has to meet certain productivity thresholds, which we can use that as technology development targets. And so, like I said, again, the 4 kilograms per kilogram per year looks like a very important threshold to meet. You're going to hear from Mike Hecht, I think, in the next panel. He's the PI for the MOXIE experiment, and so we ran a little back-of-the-envelope calculation, and MOXIE actually looks quite good right now, definitely on the right side of those assumptions. So you'll hear more from Mike. Again, let's shift our perspective from a mission by mission to this larger network perspective, and we have a very exciting future ahead in space. Thank you.
Just push it.
The right side, yeah.
Well, you have heard many exciting aspects of going to Mars and now commonality. Commonality may not be exciting, but it's very important. And in the EMC, I was assigned the task to look at something called the small habitats. I have a team that is putting together the analysis and some of the cost savings that we would achieve by looking at commonality. And let me share that with you now. This is our universe. And again, Jason mentioned earlier that there are kind of two classes of habitats within the EMC. There's a large habitat, which is a transfer habitat, and a surface habitat. Then we have a group of small habitats. When we look around Mars, we'll see we have an exploration vehicle that is pretty much looking at the Mars moons, and then we have a transfer taxi habitat that goes from a one-sol orbit down to the Martian moons and back. And then we have some surface assets that are in rovers, pressurized logistics elements, and a Mars ascent vehicle. So we have a number of opportunities there, but we're reaching back into cislunar space, grabbing early opportunities to basically enfold some of the things that we want to develop in order to go to Mars. So we're looking at an initial habitat that would be in cislunar space, as well as pressurized logistics elements. Now, commonality, like I mentioned, is important, and it has to lead. It can't follow. It's got to be at the front end of the program. And some say even before you put an acronym there. So we see it, and you can see underneath that our programmatic V, that commonality is intentional. We're not going to get it right. Earlier it was mentioned that you got to start with a certain level of decision making, and you refine that as you go on. You don't inhibit that. You move on, and you refine it. So we want to be front end, and then you've got to press that game. You can't give up. It's not fire and forget. It's a matter of being able to maintain that institutionally within the whole campaign to actually achieve the benefits of commonality. And management is key. If they're not on top of it, it's not going to work. We love to play around with the physical part of this, but it really is a programmatic decision. Now, I show a bunch of those programmatic Vs. This is how the problem was given. Each one of those elements you saw initially had its separate DDT and E. How many of you know what DDT and E is? Okay, not a whole lot. I didn't either when I first started my career, but I've got an appreciation for the first 10 years of space station. It's this mountain of stuff you have to do before you produce the first item. And you have to do it every single time, and when you're dealing with government, procurement, and all those other things, it's tremendous. So what we want to do is not have individual DDT&Es. We want to be able to do one DDT&E and then follow on with others that we can anticipate. It's design, development, test, and evaluation. The industry does it all the time. If you're building a washing machine, you build one, the rest of them are pretty cheap, that's how you make your money. We don't do a very good job within our space programs. Now, why would we want to do commonality? Obviously, we want to have that one DDT&E and then some delta DDT&Es off of that, but it does reduce cost, improve safety, interoperability. The time frames that we're seeing here for actually doing a Mars campaign, you're not going to be trained to fly some of those things. It's going to go away by the time you get there. So we want to be able to have this interoperability across the various elements there. Reduced logistics, big, in that we have fewer parts to service that whole array of elements. Simplified infrastructure, and we're leaning on a lot of the things that are done on the Earth in order to simplify that. And then training. You know, if I'm trained on one, I can do the other. So those are obvious advantages. Some of the disadvantages are that we sub-optimize. And when you're in the engineering domain, you find out that people scream. They'll nod their head when you say commonality, but not in my neighborhood. When you start optimizing a Mars ascent vehicle that has a very high gear ratio, say, I want that to be as lightweight as possible. And you don't go adding commonality. We're going to have to do it because there's a higher level architectural objective that we're trying to achieve. And in terms of technology, are we smart enough to do this? Again, with the time frames that we're dealing with on a Mars mission, we want to be able to have the latest technologies that can play part of that game. And you see some charts across, or images across the bottom, from the 70s to space station that started off with common modules to our intermodal system, which is a good model and one we're looking at, where whatever is outside of those structural attach points is independent. And I can start stacking them on ships, putting them on the road, or on a railway. So we're looking at that to simplify how we stack up our elements and fly them to Mars. Now, across the top, you see physical, functional, acquisition, and management. These are some of the brackets that we look at for commonality. Like I said, we're attracted to the physical. And in terms of the functional, that would be like having a 12-volt system. I can put different batteries in there. It doesn't have to be the same size battery, but I get the same function out of it. Acquisition and management are key. Those are the ones that really make this work. So can we arrange to be able to do our single DDT&E and arrange the procurement so it'll support that, as well in terms of the management of this overall program. So the emphasis is on the other side, and probably the less visible and exciting side, but the part that's going to give you the savings in terms of money. Now, when we look at it, our landscape in the upper left there is, let's see, how does this work? Oh, here it is. Using the wrong one. Up here, that we don't want to have a whole bunch of separate DDT&Es. This is what we really are looking for. We're looking for a single DDT&E and then all of the other elements that follow. And because we're a campaign, we're not going to go there just once. We have some second units, 2 MAVs. We have other elements that we're looking at. So we have some recurring elements out of each one of these. Now, in order to assess this, we don't really believe a lot of our parametric cost models. So we want to go back and look at historic flight programs. Apollo is good. We have 2 elements, the command service module and the LEM, that actually flew beyond low Earth orbit. They were small cabins, things that we're looking at. What were their costs? And what was the recurring? $26 billion versus $900 million for recurring in the command service module, $14 billion versus $700 million with the LEM. We want to be able to do the same, if not better. So, these are good numbers. You can trace them back. You can escalate them to, our year dollars now. The other savings is the potential of compressing the schedule. So, you saw the schedule there and how we'd be able to shorten that. We've got some tools that we're using. We've got a commonality analysis tool that dips down into the master equipment list of each one of these elements. We have subject matter experts that are supporting that to assess how do we really come up with commonality. Is it always worst case? Does the heaviest always win? We hope not. But in some cases where we have to embrace commonality, heavy does win. But there may be other strategies. This is just our first attempt to being able to use a tool and get the data from each one of those elements. You see some of the images over there on the right that are a collection of piece parts. That's our goal, so that we would be able to come up with a pressurized cabin that can accommodate all these different functions. And you can see those rendered below in terms of their specific application from an ascent vehicle to a rover. So our objective in the lower left there is to capture commonality at this front end, knowing that some are going to add on to that and others are going to take away. But there's going to be a bunch of other things that we will not know enough about early on in the program to predict. But nonetheless, that's what we're trying to do. Now, we don't start cold. We always have incoming things. We have heritage in the sense that we've got ISS, we learned from that. We also have Apollo and Skylab. Useful lessons learned. Some of them not always good, but nonetheless, lessons learned. And we take that, and then currently we're developing things like Orion. It's going to be part of the program. More importantly, Orion has a docking system on it, and if we look through our whole campaign, we have to deal with that docking system because that's the bottleneck. We've got to push things through that hole, whether it's Mars samples that we bring back all across the system. So we're saying, how can we carry some of these things forward? And the standards allow us to divorce the end solution, but still keep the infrastructure. It's like a two-prong outlet. You know, I can use that today. It was invented many, many, many years ago, and it doesn't care if it's a toaster or a computer that goes into it. We're still using it. So some of these things are standards that we can develop that are divorced from their end product. And then we start to embrace some of the planned technology developments for us going there. So that's part of what we're doing in terms of commonality. And to introduce you to some of the details that we're working on, we have vehicles, some reside only on the Mars surface, like the rover. Some transition from the Mars surface, accelerate, and go up to weightless environment. Some are only in the weightless environment. Now, there's a challenge in terms of trying to achieve commonality across these different acceleration environments. Also, what do we capture in terms of the time? How long are the crew in here? We have sawn this off at 14 days, but nonetheless, at other points along the way, there are these step functions in terms of mass. When do you need a commode? When might you need exercise equipment? So we want to know where those are in terms of time so that we can start to get the smallest cabin that'll serve all of the crew in these different situations. Sometimes we have 2 crew, sometimes we have 4 crew. And then also, since we're a small cabin, the interrelationship with any of the spacesuits is critical. They take up a lot of space, they're heavy. These kinds of things are important for us to understand. We're also looking at the pressure vessels, trying to shrink that down and knowing what is effective about those. The barrel section is a lot easier to package than these compound curve end domes. So we want a longer barrel section and kind of squat end domes or end cones. And again, this is where we start to sub-optimize the structural portion of this. But it gives us a friendlier geometry for packaging. Horizontal or vertical, we've looked at various ascent vehicles in both configurations. Most of ours are leaning to be horizontal, so we're choosing that as a starting point. We can come back and revisit it, but nonetheless, that's where we are now. And then internally, we're looking at a range of things that shape that diameter, trying to shrink it down to the minimum size, whether it's, you know, the posture in those particular environments, whether it's attaching suit ports at one bulkhead and being able to get in and out. We're beginning to shape this thing and bringing in data that would allow us to have a comfortable starting point. And then, in terms of our initial starting point, we hold it loosely. We're willing to revisit it. We're willing to change it. But we start with a small pressure vessel we tailor the endomes. And the benefit of this for our commonality is that I can develop that interface, and I can now contract out separate endomes. I can do it in parallel or over time. And then I need to have the connection with the rest of the overall campaign. So we're dealing with our adapters that connect up to these. This is the campaign architecture laid out in, when we need these particular elements and when they fly, and when we need to have commonality decisions. You can see that there are some that fly very late, but nonetheless, that information has to come up when we start making commonality decisions. So this is our challenge, and we understand it, so we'll make certain decisions, but it's not a matter of withholding those, otherwise we will not have a common system. There'll be separate developments across the way. In a thesis that was done at MIT, this is a graphic version of the text that was there. There are several ways of actually implementing this. The one there on the left, the reactive reuse, would be like the old Skylab. I'm ramping down, going to the moon. I want to do something else. Here's a propellant tank. I'll turn that into a habitat. The other is the common building block, or an assessment of high-value items, and then being able to select those, and you do a build-to-print or a supply as GFE, government-furnished equipment. Now, the reason we're doing this is because we can't do onesie-twosie and achieve commonality. We can't say, I want a pressure vessel in year 1, year 4, and year 8. There's no economy in that. So we realize what we can do here in order to try to achieve it. The other thing that's programmatic is build in life cycle cost incentives into your contracts, and then hold those contractors accountable. And then you need strong systems engineering, that was mentioned earlier, and strong management. This has got to bubble up to the top and be able to be reinforced by that. So when we close out, those are the images of the different vehicles as we are today. And the only reason we're doing this is to kind of validate our commonality assessment and being able to see if these indeed can be common. But there'd be great economy in being able to have not only the Mars small pressurized elements, but also in the Lunar campaign, be able to demonstrate some of the things that we want to do in Mars and realize the economy early on in the program. So that's the end of my presentation. Candace? Thanks.
Okay, yes. All right, so as Jason mentioned, I'm going to talk about the mission cadence and how that factors into the sustainability and affordability of the campaign. So within the Evolvable Mars campaign, we are exploring multiple pathways in order to meet the 2010 NASA Authorization Act and Space Policy of humans to Mars in the Mars vicinity of by 2030, excuse me. So all of our pathways start in LEO with utilization of the ISS to the greatest extent possible. And then we move on to cislunar, where we're utilizing lunar distant retrograde orbits, or DROs, as aggregation for beyond LEO missions. And then we come to the decision point of Mars vicinity. Where are we going? And as you can see, we can look at Mars orbit, Mars moons, or Mars surface, or some combination thereof. And we can also support our international partners and industrial partners by going supporting their missions to the moon. In addition to these when we're doing the multiple pathways analysis, we are considering the strategic principles that Jason mentioned earlier, such as the cadence of the SLS and Orion to support a sustainable cadence, and then also reducing the number of unique developments. We're trying to utilize test and validation missions as pre-deployments and pre-emplacement missions for testing of these capabilities. Through looking at multiple pathways, the one benefit that we gain is that we can understand the common capabilities and the need of these capability dates. Some of these capabilities will be driven earlier in a campaign, and some will be driven later in a campaign, and these obviously lead to decision date needs. As we see in the chart, we move from, in the Earth-reliant phase, we're utilizing the ISS, which I mentioned, and then we move on to the proving grounds. Within the initial proving ground phases, we have capabilities such as SLS and Orion and initial cislunar habitation. in addition, the asteroid redirect vehicle is an enabling capability. And then as we move further through the proving grounds, block upgrades of the SLS, the advanced propulsion, upgraded block SEPs, and then long duration habitation are key capabilities. And then finally, as we move towards Earth independence and into the Mars vicinity, additional upgrades to our SLS, and then things like the entry, descent, and landing required for Mars to deliver large cargo and crew, and then long duration surface systems. We also have things like ISRU and how they are key in playing into the transportation architectures, which Ali talked about. And then as we develop these capabilities, we complete the missions that are shown on the bottom of the chart. In that, and the goal of the missions are to do Mars risk reduction, ultimately leading to Mars missions, whichever they may be. Within the proving ground, we have several objectives we'd like to achieve. Again, testing SLS and Orion, using LDRO as a staging point, demonstrating the deep space EVAs, the human robotic mission operations, evaluating the crew health and performance, obviously demonstrating the SEP, in situ resource utilization, reducing our logistics chain from Earth, and long duration deep space habitation. The capabilities that we're planning to develop within this proving ground are the SLS and the block upgrades needed, the Orion, the initial deep space habitation, the deep space EVAs, and the reduced logistics chain. In analyzing multiple pathways within the EMC, we've utilized the split mission concept. Here we use the SEP to pre-deploy cargo to the Mars vicinity. It's approximately a 2 to 3 year transit. We're minimizing the cargo that's sent with the crew, and thus we're getting a better cadence of the SLS launches throughout the years. And we also allow for pre-positioning of the assets for checkout prior to committing the crew to Mars. For the crew vehicle, we're doing aggregation in LDRO. The benefit of LDRO is there's no station keeping compared to L1 and L2. And also, it allows for access for testing and checkout of the habitat and the vehicle before sending the crew. The crew then, the vehicle then transits to LDRO or to an LDHEO to meet up with the crew, and then the crew and the vehicle depart for Mars. And as for the crew returns, after the Mars mission is complete, the crew will rendezvous with the Orion, and then the Orion will split off from the deep space habitat. And as Jason mentioned, the habitat will return to an LDRO so that it can be refurbished and reused for later Mars missions. Because in the Mars systems, we're looking at multiple pathways, and we haven't determined staging points and aggregation points. There's several destinations to think about as pathways. If we choose to go to Mars orbit first, some of the objectives are we can accomplish real-time teleoperations on the Martian surface, obviously demonstrate the split mission Mars concept, and then some of the validation of the transportation long-duration human systems required to go to Mars and the human stay capability in a zero micro-G environment. So the capabilities required for the Mars orbit are all the proving ground capabilities plus an approximate 1,000-day deep space habitat, the high-power SEP, and then deep space countermeasures to ensure the survivability of our crew. For the Mars moons, some of the additional objectives include utilizing the Mars moons as, for additional radiation protection while in deep space. And then in addition, the prospecting and demonstration of ISRU on the Mars moons. So the capabilities required for Mars moons are all the Mars orbit capabilities in addition to Mars vicinity propulsion. So this would be, depending on your staging orbit, transferring back and forth between the moons in that staging aggregation orbit, some destination systems, and some Mars moons habitation. And because we're driven by trying to minimize the number of unique developments, one of the direct transfers of capability here was on the ARM mission. The hopper legs and the habitation legs could be envisioned to be very similar capability. For Mars surface, some of the additional objectives would be obviously testing the entry, descent, and landing of the surface infrastructure, utilizing the local resources, the Mars surface as radiation protection, routine EVA and dust mitigation, progressively leveraging the ISRU on the surface, and then the return and reuse of infrastructure at a single exploration zone. So this is important that we're focusing on looking at crews returning to the same exploration zone. The capabilities here required for the surface, in addition to all the Mars Moon's capabilities, EDL, surface mobility, surface EVA, long duration surface systems, and then partial gravity countermeasures. So in summary, the EMC features several opportunities for phasing of investment capabilities, and that's how we're trying to achieve our affordability, by being able to phase our investments. So the first opportunity focuses on the initial proving ground, where we're demonstrating staging and various capabilities to support future destination missions. The second set of investments is phased such that it's more focused to either supporting our international partners or industrial partners and going to the moon or going to the Mars system, where the moon would require lander and short duration habitats, which we envision would share significant heritage with the proving ground elements. And if we were going to choose to go to Mars vicinity, we would require long duration deep space habitation and transportation capabilities. And then your third set would be the set required to go to the surface of Mars, including EDL, surface mobility, and long duration systems. So these investment opportunities are purposely built into a phasing of the mission sequencing to accommodate the changing priorities, capability maturation, and the affordability scenarios. Thank you.
Okay, so we had a couple minutes for questions, so I'll try to corral those couple questions if you guys have any for any of the panelists here. Yes, right here.
I was looking at how much space there is.
Candace? Oh,
Okay,
Brand.
Brand.
Standing up, and I was thinking, and you were thinking right. Could a Dutchman go? And that's not a frivolous question, because we're about Dutch person, yeah, Dutch ladies, but me as the big exception are like 6'3" quite easily. And if there's so little space, and it's not a frivolous question, because I know it was a problem with our last Dutch astronaut, because he was actually too tall for the Soyuz.
So you're talking about anthropometry and, yeah, okay. Actually, you know that in the weightless environment, we actually get, in our projected height, a lot shorter. But we're taller because the vertebrae expands and things like that. So we can handle that pretty much, and what we've tried to do is accommodate the full range of population up to the 95th percentile by having 2-meter separation between decks. That seems to work in all gravity environment. We don't know a whole lot about the moon or Mars, but we assume that that'll work and capture the whole population, both extremes, male, female.
Other questions in the back here, the center?
Capabilities. So how much do you look at things like plug and play, for instance, as a way to evolve technologies without maybe driving all the cost? Testing evaluation.
So Brant, do you want to take that? I mean, I think the question, let me summarize it since we didn't have a mic, is commonality versus plug and play. And there's two different ways to look at commonality. One is where the predominant portion of Brand's presentation is commonality in that sense. The other piece, I think, is where Brand was pulling on with standards. And standards then allow plug and play. So I think,
I think that's a very good way to put it. If I were to take my old CRT TV and I gave it new avionics behind it, that wouldn't accomplish much. Now I've got a new display and I have, a higher upgrade electronics behind it. So in some ways we can only predict so far, and if we can keep our architectures fairly open, then that'll be best. Then like a lot of missions now, we're not really through with the software. We launch it, we upgrade it, we can reprogram in flight. So we've got to take advantage of those capabilities in order to deal with an adjustment. At some point though, you're going to cut metal, you're going to freeze some things, and you're going to live with it. And it may not be altogether bad. I mean, we don't always have to have the latest technology to do things. So I think getting there and balancing the cost against having dependable systems is an important game to play.
A couple of announcements that will lead into a final question. The moderator gets to, or the session chair, you're the moderator, gets to do this. First of all, the announcements before we break. When we return, we will return, we'll abbreviate the break a bit so we'll get back on schedule, returning at 10:45. Will the folks who are on the next panel during the break go back and be mic'd? So again, 10:45. Last question, this is for Ali, which is a very impressive presentation of all the nodes and logistics and so on. You favored, or in your discussion, you favored the development of ISRU as a key enabling technology, which didn't, for example, appear in the early stages of the JPL and other lean and more focused scenarios. To develop the technology for ISRU, that is an enormous expense. Your estimate of the opportunity cost, what would be taken out of a scenario like JPL's in order to invest in ISRU?
So I think ideally we shouldn't think of it as one or the other. I mean, the best way to do ISRU is to co-develop it as we do other missions. And that's why I think the MOXIE is such an interesting experiment, which is, you know, it's a real collaboration between human exploration and space science and technology. And let's see, MOXIE is a very focused, you know, solid oxide electrolysis, getting oxygen out of the atmosphere at Mars. It's going to get vented, actually, but maybe there could be a scaled-up version of MOXIE where we actually store the fuel and maybe use it for a small ascent stage. Maybe not for humans, but maybe for sample return.
Sounds expensive to me.
Well, it may be, but the idea is don't think of ISRU as something completely outlandish and as a separate. You know, it's got to get integrated with other things we do anyway. And the key is that over time, the returns are going to be humongous. Okay. And eventually, like many things on Earth, we heard this, you know, the government can't pay for everything. What we want to see eventually is a resource economy in space. We want to see private enterprise running ISRU. We want to see mining. We want to see fuel depots. And maybe one day there'll be a fuel depot in DRO, and there'll be 3 different missions bidding for the fuel that's in that fuel depot. And the highest bidder gets the fuel and gets to do their mission. That's not going to be by 2040, but maybe 2060, 2080. That's where we want to get to, and that's what ISRU will enable.
You still will all be back at 10:45. Let's thank Jason and Ali and Brand and Candace again.